Okay, we're live.
So, Kurt, do you want to start?
Sure. Are you ready? Are you ready, Joe? We could start a little early.
You are on mute, I think, Joe.
Thank you. Usual user error. No, no problem starting. Let me just make sure I can share.
Kurt, you said you want to start by putting up a slide that has everyone's name on it?
Yeah, I can't get that to work. I select it and it won't let me select it. So we'll just go ahead and start. I'll see if I can open it up in a different yeah. Let's not worry about it. Joe will introduce himself. It's on his first slide.
Yep, I'll go ahead and share. Make sure you guys can I'm gonna go ahead and are you able to see? Now I can't see you guys. Hold on a second.
Yeah, the share is full screen.
Okay, so you're able to see. You're able to see TI IoT solutions.
Yeah. Yes.
Okay, now I can see you from on the other side. So thanks everyone for allowing me to talk. My name is Joe George. I'm with Texas Instruments. Been for years, since the 1990s actually. I'm actually a MIT alum, class of 90, 91 masters. So I appreciate everybody getting on here. Haven't talked in a while to Kurt. I'm glad he reached out and said, yeah, what's going on with Texas Instruments IoT. So decided we'll go through some of the opportunities and some of the devices that are out there, give you sort of updates. All this is actually non-NDA information. I think we've actually labeled it selective disclosure, which means, I wouldn't put it on the external internet. There's nothing proprietary, but nothing wrong with, sharing around, emailing it around and such. And you need more data, we can always give you NDA if you want, stuff in more detail. And I guess I should have put a better agenda slide in here, but basically we'll go through an adventure of basically IoT solutions from a TI standpoint. Wrong side there. So the first place that often we see IoT, and I'm going to blast through this a little bit, is Bluetooth, and especially Bluetooth LE. People like using Bluetooth LE. There's a bunch of CC devices out there, and this is actually a soft marketing release that we're having on a CC23-4X family. This actually, and I like to highlight, is supposed to be a sub $1 device that gives you, and let me, oops, gives you the ability, and you'll see this sort of slide from TI, one of our VPs that started a couple years ago wants almost every business unit to have this type of slide that gives you just a snapshot of what the particular features are on a particular TI device. But this is a Cortex M0 based, system on a chip, Bluetooth. You might have seen other devices out there, CC26 family, CC25 family. This is our, again, very cost-effective, small package type device that we're coming out with. Simple Link is sort of the terminology we have for here on this particular SoC. And then on the next slide, we do have, and again, on the website right now, I'm going to blast through some of the animations here. You can go to the CC2340 website on TI, and it'll give you just do a search on 2340, and you'll see sort of a teaser on some of the features of the device that are out there. If any questions or comments on using Bluetooth, and the whole point here is to make Bluetooth very cost effective and be able to sort of put the BLE down anywhere, with of course major power savings opportunities. So next to Bluetooth, for IoT, of course, and people at first say, "We'll never do it; it's too much of a power hog." Would be sorry, between the two windows here, is Wi-Fi. And at first you'll look at this and go, "Oops, click too fast." At first you'll look at this and you'll go, "Oh, this is a great roadmap slide. Joe, why are you wasting my time with Wi-Fi 4?" Actually, you guys can't. Oh, there we go. There's my cursor. Why are you? You can see my cursor, okay?
Yeah, your cursor is fine, Joe.
Why are you wasting my time with Wi-Fi 4? Let's go to 802.11 ABGN. How about Wi-Fi 5 and 6 and 802.11 AX and 8? And we'll get to that in a second. The reason we're showing this slide actually is sort of academic to sort of mention the types of Wi-Fi devices that are out there. Very similar to the BLE SoC, we have what we basically call a Wi-Fi MCU. But at the same time, too, there are devices out there, and the Wi-Fi MCU will have, in this case, Cortex M4, along with a radio and such, and you can run, your Wi-Fi stack. But sometimes you don't want to use, the MCU that's on the particular Wi-Fi. You just want to add Wi-Fi. In that case, we do have Wi-Fi network processors, and you can add that here, the network processor. Usually UART or SPI connection to whatever MCU or MPU that you have, and you basically get a TCP/IP stack and everything running on this device. And these, though, on the IoT world, there are usually lower speeds, again, to save power. So you might be 50 megabit, 30 megabit, those type of, even though it is whatever Wi-Fi standard. When you want the faster speeds, then we get into more Wi-Fi transceiver. That's often a separate chip. And some of you might be familiar with the Y-Link world, which we've had for a while. It originally came from the cell phone world. So not only does it take care of doing your Wi-Fi, it also gives you Bluetooth and deals with coexistence and such. Since you're running 2.4 gigahertz both, and don't want to have too much congestion between there. So this is basically our Wi-Fi 4 portfolio. And just to give you a closer look at what the block diagrams look like we mentioned. Here's our our SimpleLink again, where we said is a system on a chip. It's got basically the application processor, which is the Cortex M4. And again, here's our network processor. Actually, I should run the animation on here, where basically the network processor, can run just this network processor you get by yourself, or use the MCU, in this case, the Cortex M4, or as you see here, this ends up being the transceiver by itself. So those are sort of in two block diagrams, the three devices, or the three configurations that we talked about. But what we're going to do in the future, and again, real quick, we mentioned the 20 to 30 megabit is what you normally see for the SoCs and the network processor, again, with good power savings. The Y-Link here does come from the cell phone world, so but we do get around 100 megabit along with the Bluetooth, and again, decent power savings. But the next generation, of course, that everyone is asking about is not the Wi-Fi 4 that we're talking about, 802.11 and such, but going into, and let me blast through the rest of the animation, Wi-Fi 6. And you go, wait a minute, Wi-Fi 6? What happened to Wi-Fi 5, 802.11 AC, or Wi-Fi 5 here? We actually, TI decided not to do a device in that because it really wasn't IoT friendly. It's more enterprise based, and it didn't really have the the power savings and stuff that we needed. And so what happens with Wi-Fi 6, and we'll get to the next slide in a second, you'll see lower latency, you'll see better power numbers and such. And just like 802.11 N and such, we got 2.4 and 5 gigahertz. But when we get into Wi-Fi 6, there's also 6 gigahertz band. And of course, things like security, WPA3 actually goes all the way back to N even if needed. And realize too, the 802.11ax, it is compatible with AC, again, giving you a lot of power and latency advantages. Any questions? Oh, actually, more interesting probably into the sort of marketing slide is a bit more the technical slide, right? Showing, again, 802.11 N, which was pretty much, oh, I'm sorry, Bob, did you have a question?
Okay, I think I've turned it on. Can you hear me? Okay, could you hear, is this working?
Yep.
Okay.
Yep.
The big thing for IoT at this point is everybody's doing 2.4 versus pricing. So if you could say something about pricing.
Not exactly. I mean, there's definitely prices for the Y-Links up there. I mean, you go to the TI website and just type in, actually, let me show you the part number back here, WL.
Okay, you don't have to answer it, but I just want to say, when I'm looking at things, that's the number one issue I see. The people make it. You need an ESP32 equivalent with with the new Wi-Fi.
Okay, no, we've definitely heard, and that is our intention is to get to that level. We're probably not at that level with the Y-Links and WL1837, which I don't see here. It's probably the superset.
Okay, you don't have to belabor, but I just want to make that point because it'd be very exciting to do that.
So that is the intention, and again, oops, I went too far here. You'll see a device coming out probably middle of this year. Again, I had to give you stuff that was non-NDA at this point, but I can hint you'll see something in this world right here, and the intention is definitely to have that be, sub.
Okay.
I don't know if I can say sub. Low price.
Let me just leave a link. I'd like to have an NDA discussion with you on that because it's directly central to things I'm trying to do. And I think there's a lot of synergy there.
Okay, gotcha. No, we definitely do. Just out of curiosity, what is the price that you're seeing now on the
$2?
ESP32? $2. Okay, I think we're going to be in that range, if not better.
Okay. So if you can do that, you understand the market.
Yeah, no, and that's definitely an intention. Quick question there. What's the bandwidth on that? I assume
I don't
for
care.
$2, you're not at 100. You're not at a gigabit or something.
No, the whole point of this is to turn on a light and stuff. These are very low traffic applications, but vital. Yep. So that's the exciting part. And I'll just say, and we'll discuss later, I'm very interested in the software as things like Tasmota, Shelly make it much more programmable than the typical embedded system world.
Yep, and what we've done actually is what'll happen on the transceiver. Let me go back to here real quick. If you go on the transceiver side, actually, and you'll see the interaction with our NPU in a minute. Sorry, one more. It's just going slow here.
Okay, again, you go back to talk, but I just want to say I want to talk to make sure that it's a software platform as devices like the Shelly turn hardware into software.
Yep. No, what's going to happen? Oops. Did I just crash? Great. I think my presentation just crashed. Let me get up again real quick. But what is the Simple-Link side? It's a very simple SDK, and on the transceivers, and even now that you get in way, when we get to the transceiver side, and again, it's actually on the what do you call it? On mainline Linux, you'll be able to get the drivers and such. Or you'll be able to get the future Wi-Fi 6 drivers also. We go to it now.
Okay. Again, I don't want to distract too much, but I'll put it this way: TI missed an opportunity with the watch. I don't want to see them miss it this time.
No, I'm sorry.
What? It keeps dropping. I keep.
No, I'm sorry. Which? See trouble, a little spin. I guess you can see my Google screen, but that's about it right now.
Yeah, the first thing you should do is always do Windows D to hide everything.
Oh, sorry, sorry about the technical here.
By the way, I assume you're local in Boston.
Sorry, I'm going. Here we go. It's opening.
Looks like we lost him.
Oh, well, what a tragedy. He'll be back, I assume. Is he local, by the way, in Boston?
Yeah, I'm pretty sure he's in Arlington. He certainly doesn't work in Texas.
Okay, good. Because I'm actually excited about having a next generation of chips, but we have to make sure we get the software there.
Yep.
I had a question real quick. So, just can like I've been looking IoT wise. I've been looking for like a cheap transceiver that can transmit at other areas of the spectrum, like below 2.5 gigahertz.
Why?
Mainly just for ham radio stuff, or just to play with digital modes like APRS. Yeah, and like I've been looking online, but I didn't know if anyone had any suggestions.
I think there are some SDR platforms. I haven't looked at it myself, but I think there are some relatively low cost SDR based.
Yeah, looking on in general, I think most of the solutions I've seen are just receiver based in terms of SDR, but it seems like really hard to find an SDR based transceiver. I know a lot of people do is that they just use an external one and just plug it into their sound card, and then do the analog to digital conversion on their computer.
Yeah.
By the way, the picture behind you, they're going to start calling that a monocopter as a retronym. Oh, Joe's back.
Sorry about. I'm back. Sorry about that. I luckily didn't have to reboot, but not sure what happened there. So all I was saying, Bob, is so the intention here, software-wise, SDK for the SoC and the network processor. They'll hook up to other MCUs if needed, and then here on the transceiver side, we're in mainline Linux now with the WL1837 or the others.
Okay,
future device also within mainline. I'm sorry.
We can have a geek talk. I don't know whether this is the place for it, but we should just get together and bring up to date on sort of my exploration of the ESP32 world and the two worlds. There's the old embedded system world using them, and there's a new sort of software device world.
Okay, definitely curious to hear that.
And to answer Bob's question, that is a helicopter that's been restored. It was in my company in Vietnam. I actually flew it at one point.
Oh no, I appreciate that, but you also appreciate the retronym. Whereas everybody knows about quadcopters more than helicopters, so they have to call these monocopters.
That's true.
But yes, it's
Okay, Joe, you're back up.
So continuing on with the Wi-Fi 6, not only will we have the 2.4 and 5 gigahertz, but also Wi-Fi 6 is also going to have a 6 gigahertz band. Of course, anyone who took any of 6013 or 6014 knows that anything RF, right? You're going to basically, as you increase your the frequency band, you're going to have less range, which is always a trade-off. But hopefully, anyone in an apartment complex, no one knows how to run a 6 gigahertz access point. So you'll hopefully be the only one, on that particular frequency.
Actually, this raises another important question. Wi-Fi 6 power management. Are we going to be able to get adjustable power?
Yeah, that's all planned. Just like honestly, it'll be a model like the Y-Links in the same way.
Okay, good, because that's another issue with Wi-Fi. Good.
Yep, and that's why we are concentrating this on for IoT, right? And again, why we sort of skip DC world.
It sounds like you're doing everything right, so that's why I'm excited to talk.
Yep.
Can we do it at the command? Can we do it at the command prompt, like IW power settings? For
Linux, yes. And then for when you look at the SoC, again, there's a whole SimpleLink SDK that you run, sort of from a main.c type of thing.
Great.
And then continuing on the Linux side, though, if you're going to run a transceiver, you want some type of processor to run it with, right? And for those of you that are familiar, and I'll show the diagram in a minute later, with the AM335, which has been out for about 10 years now. Beagle Bones, all kinds of Beagle, etc. Very popular device from TI. We're finally now entering the 64-bit world. And this device is out there that you can actually get right now, the AM62. This is now the starter kit EVM from TI, but there are Beagles on the way, such that it'll be even lower cost. And one nice thing we've done with the starter kit is that not only are we giving you the 64-bit processor, and again, of course, all the all the other HDMI around it, so it almost looks like a Beagle. But I guess you can't see it well here. But there's also, in this case, a Y-Link on board, a WL1837. And you can imagine that, once our Wi-Fi 6 solution is out, you'll see a board that also has the Wi-Fi 6. And again, with the mainline, well, eventually it'll get to mainline Linux. Honestly, obviously, initially you'll have to download a patch or something. But that hand in hand. How much memory on?
So I'm assuming this is a chip with the CPU and the Wi-Fi and Bluetooth.
No, this is actually a single chip. But actually, let me go to similar to the AM335. The AM62 is basically up to quad core type of thing. It's got, I don't know if anyone's familiar with PRU, the programmable real-time unit, graphics engines.
It's a complete system. Yes.
Yeah, it's a complete system digital chip, right? But then the Wi-Fi will be separate. Obviously, the memory is separate. I mean, there's RAM on board and caches and such, but then you'll be running, actually going back to here, you'll probably run out of, some type of PMIC, some type of codec. Oh, here we go. Actually, they prefer, so DDR will be your volatile memory, and something like an eMMC or even SD card is what you'll, boot off of. I know the Beagle Bones, we've been doing eMMC. I'm not sure what our future Beagle is going to have. But nowadays, too, we're starting to put quad SPI flash, and we'll see in a minute why we've got quad SPI flash here on top of, other non-volatile.
Hey, Joe, are you sharing your screen? We don't see it.
Oh, you can't see? Are you, the screen share go away? Let me do it again. Are you able to see it now?
Yes. Thank you.
Oh, sorry about that. So you saw this slide, right? Previous.
Mm-hmm.
Yeah.
Okay. Yeah. So right now, basically, we have the 802.11n, transceiver. You'll see the 802.11ax come out, and right now, keep going too fast. Right now, you're able to get the AM62X starter kit. Even we said again with the Y-Link, and you'll see that, which is the Wi-Fi 4. You'll see the Wi-Fi 6 coming out. And here's the memory we mentioned, right? So here's a DDR4 for non-volatile. For volatile, and then either eMMC, micro SD, or we'll talk in a minute why we have a quad SPI flash here potentially. And of course, just like a Beagle, we have HDMI. That you can use, connect USB if you want. And, I have sitting in the lab right now, one of these set up, actually running a version of Chromium. We want to do some animations and such on Chromium. So we're using that right now in our lab. And by the way, most of these things are now all powered by, some WSB power. This sort of got more popular. So, and where this comes from is sort of the Beagle world was AM335, right? This is the 64. This is a 32-bit ARM. Now we've got 64-bit ARM. Well, this is what I was mentioning earlier. Up to quad core at this point will be the superset, but also got cut downs. And this is sort of differentiations between the AM335 and the AM62. The big thing, of course, is the 64-bit core. But a lot of the other stuff is sort of a almost a PC on the chip type of thing. So continuing on, no chip is good if you don't have software, right? So out of the box, we've got Linux, obviously. This is a slightly old slide, actually. Android is available now, and also real-time Linux, all available now. So it's a slightly old slide. But one point that I wanted to bring up, which maybe I should have gone on the slide before, well, here is that when you look at the AM62, and we didn't do as good of a job of this on the AM35, you've got the Cortex-A running processor SDK in whatever particular Linux. But we also have MCUs on board, and you go, MCU, where did I see an MCU? Going back to this block diagram, some of this is coming sort of from a safety world. We have right here a Cortex M4F, and FFI actually stands for free from interference. And the whole point of FFI is this Cortex M4 is running as a separate MCU, completely independent power tree, internally, right? Power tree resets, etc. So your Linux can crash, and even if it does, your Cortex M4F is still running. And so this is sort of coming from a little bit, honestly, from the automotive world, where we've also got R5Fs on certain devices. This particular one is the Cortex M4F. And so how do you program that along with the Linux or RT Linux or whatever? That's why we've split into two SDKs. We've got the Linux or Android or whatever running on your Cortex A, and then on your Cortex M, you're going to go ahead and run this MCU SDK, which is running free RTOS. Some versions do have a bare metal. I think we're pushing more people to use free RTOS as things get more complicated. But no, so we have sort of two separate SDKs running with all these different devices that are out there. And what's interesting is we don't show it here, but we even have some interprocessor communication, mailboxes, etc. So a bunch of packages that makes it easy. And I'm not sure how many of you have seen. AM62 is the more cost-effective one. There's an AM64 device out there that's available also running this. Not as friendly when it comes to display and things like that. It's a bit more of a headless device. So continuing with the software side, this is sort of the TI world when we talk about processors. AM62 is the most cost-effective solution. There's a bunch of other families out there. Some of the R5S and stuff actually come from Jacinto, as sort of an automotive world, and that's why we do have some of these free from interference. It's more of it was a safety, and some of those have been pushed from here down to what we call Satara NPU. In general, when you think, microprocessor, right, you're thinking something that's running, hundreds of megahertz, if not gigahertz, doesn't have onboard flash typically. There's another world, of course, that we talked about, which is MCU, and we'll see in a minute what Satara MCU is. I think in general, when we use the term MCU, we mean a microcontroller, right? We expect some type of onboard flash. So even though you have all these things in your IoT system, there might be, something that needs a little bit of housekeeping, if that's the right word. And that's sort of what our MSP world is, right? In our MSP, you find, functions like you need an external RTC, or you need, some type of extra, PWM or something like that going on, or a wake-up controller, etc. So just letting you know that there are the MSP 430 families out there, again, very good for power. So, good for RTC. And you can actually find, I should put the link in here, but basically the code is readily available. Again, with this training and even an ebook that then gives you the code and the software, for basically just running this RTC function, along with a PDF and such. So hopefully making it easier to not look at these MCUs as a device, but look at them as a function that you need to get working with the rest of your IoT system. And then just showing you multiple types of packages, memory, etc., a wide variety. Are people familiar with the MSP 430 family? Around, actually, it was originally called mixed signal processors, what the MSP stood for. It was a big deal back in, it was actually TI Germany that came up with adding A to Ds and such on a microcontroller. But something else that is sort of a soft release that we're doing is some customers have looked at something, we don't want to use a 16-bit, TI. I hate the word proprietary core. I think it's a non-standard core. They say we want to use an ARM. And again, we showed you this. We've got all the collateral and development kits and et cetera for MSP 430. But we also have coming out what we call the MSP M0. And there is a soft release. You can actually go to like MSP M0 L1305. You can see the data sheet right now. And what that is basically Cortex M0 that's in the MSP infrastructure or whatever you want to call it. So very low power, use the same TI code composer, but now it is a 32-bit ARM instead of a 16-bit 430. And I actually like this slide because it actually shows you sort of the breadth of TI processors that are out there. The high-end NPUs we talked about, right, that have some type of virtual memory manager, and you can run Linux and high-level operating systems and such, all the way down to this is supposed to compete. And again, you can go and see the price on this 1305 is pretty down there. But start to compete with sort of those 8-bit MCUs out there. So in the middle, and I hinted about this before, you see something called a Satara MCU. You go, what the heck does that mean? An MCU means you had onboard flash, but then a Satara, from what we understand so far, is an NPU. What is that all about? And this is a device that's come out, and actually AM2434 is one you can go look at right now. And that's basically, think of it as an AM62 that doesn't have the Cortex A. And instead, what we're giving you is a bunch of the Cortex M to R's, depending on this device. You can see the same M4F is here, but there's no Cortex A here. You're not going to run a high-level operating system. Instead, you're going to, basically but a bunch of MCUs to run, again, PRU and a lot of the other peripherals that you've seen. And the beauty of this is you're running, at this point up to 800 megahertz. So this is a very powerful MCU running free RTOS, not running Linux or anything. Again, some of the same interprocessor communications. And by the way, when that Wi-Fi 6 comes out, you'll see not only are we running in Linux, but we're going to run basically a Wi-Fi 6 off of one of the Cortex R5s if you want.
Just a side, I like not having to put up with a stupid operating system.
Yep.
I mean, getting to the
sure. And
iron is something I do periodically. So very good again.
So you have the choice to do it either way. What you'll see is if you're using M24, we got the little launch pads. We'll connect to a booster pack, or again with the SK, there's an adapter. Eventually, will spin you on board, but it gives you the ability to do Wi-Fi again with lower power. And compared to an MSP 430 or something, you've got some serious peripherals and such here if you need quads. Oh, and by the way, that's why we have an OctoSPI that we've shown here, but that's why you have a quad SPI or OctoSPI. That's for booting up the MCUs. And the last slide I had to show, and I'm glad, I'm pleasantly surprised, but I don't know, or appreciative. No one's bugged us about supply, because that's obviously been something that customers have had problems with the last couple of years. And I've got a link here for you. You can see the fact that some of this digital stuff, even the AM335, TI acquired a fab from Micron actually in Utah. That's actually in less than a year up and running. They're actually already spinning, I think it's C2000 devices out of there. Obviously, we've got Dallas, and you have to go to this link here because these are all digital, pretty much in this case connectivity. But even there's some analog new fabs in Sherman, Texas for them going to be built. So actually, if you go to this link right here, it talks about Lehigh, but if you go to the bottom, you'll see there's more talk about other TI fabs that are coming out there. So this is all basically TI capital that we're using to basically build fabs and not have any supply issues anymore. So wondering if you had, that was it for me. I don't know if you have any other questions or comments.
No, this was great, Joe. I think what we might do, Jabber is going to want a copy of the slides if you're allowed to depersonalize them and send them. Or are we allowed to get a copy of your slides?
Yeah, no, I can definitely send the slides. It does say selective disclosure. And the only reason it says that is, don't post it on like a public website that anybody can get to type of thing. But definitely sharing it amongst yourselves.
This video will be posted.
Oh, well, that's true. Oh, that's a good point.
You might want to modify that.
But it's low res though, so that's okay.
Okay.
Right. So,
Okay.
I mean,
Everyone
there's
else- yeah. Send me your email address. So to blue@bob.ma.
okay, yeah, can do.
So I think we're going to want to pivot to Shankar. I wanted to get Shankar on so that he could get off at 8:00 too. If you want to hang out for a bit, Joe, we can keep the Q&A going in the chat and polls, because I actually had a bunch of questions about bygone standards. We had an IEEE mesh working group member come and talk to BLU once, and I don't think anybody's implemented that. I don't think Meraki implemented it, not the IEEE standard anyhow. But yeah, if you have to split, I know you've got some business tonight, so we'll get you and Shankar on and off so that you can go make your Zoom calls in time.
Okay, I'll be on for about 20 minutes, and I'll watch before I prep for the 8:00.
Okay, cool. Are you up?
Thanks, guys.
Are you ready, Shankar?
Yep.
Just one thing I want to clarify. Joe, did you say that we cannot post your slides on our website?
If it's an external anybody can get to, I'd rather not. That's why it says a selective disclosure. I could probably give you a version that would be very minimal. That's only the public information. I'm trying to think what's on here. Yeah, I guess there's nothing really horrible on here. It just says selective disclosure. So I mean, you're saying it's something public anybody can get to.
That is true. When it's on our website, anyone can see it.
You know what we could do, Joe? We could put a link to your blog post, because you have a IoT video on the TI blog.
Yep, no, that's fine. That's definitely a good start.
The
I mean,
reason-
if I email it to you, Kurt, I mean, you can send it to everybody on the call, right?
Yeah, we could do that. And then I'll just,
Okay.
for the public disclosure stuff, I'll just put your TI blog posting. So that's already public.
Yep, no, I think that's perfect.
the reason we like to put the slides on our website is because sometimes we want to like refer back to some meeting we had like a year or 2 or 10 years ago, and if it's external links, well, most of the time those don't exist anymore. So if it's something like but it would be okay to release it a year from now. Maybe
Well, you know what I can do? I think some of the stuff, some of the hints that I gave you guys about the Wi-Fi 6 and stuff, that's probably what they don't want up there. I could pull some of those off. You know what? I'll send you two. I'll send Kurt 2 versions. I'll send one which is just to share amongst themselves. They'll say selective disclosure, and I'll pull out some of the Wi-Fi 6 stuff out of there that that could be objectionable, and have it more clean, and that won't have anything. I mean, you can post.
with that,
Is that okay, John?
yeah, that sounds good. One other thing though, it's would there be any possibility that maybe we could have a copy of it that we don't post for a year or 2 until it's okay?
Probably, yeah. Once all these devices are released, yeah, I mean, that should be done. Then you can put the selective disclosure. At that point, it'd be old data. So, because all that will be on the external website.
Okay, that would be great. Thanks.
Okay, no, I'll mark it that way. Yep.
Okay, so now Shankar can do his stuff.
Thanks, guys. Take care.
Okay.
I mean, I'll be listening in without the video on.
All right. Can you guys see my screen?
Yeah.
Yes.
Yep.
All right. Okay, so for those that don't know me, I'm Shankar Viswanathan. I work at AMD. I mostly focus on performance architecture stuff, but I've also dabbled a little bit in security and some of the software stuff. And this topic is somewhat tangential to the overall theme of IoT, but just something that maybe some of you find interesting in how these SoCs today are effectively all multi-ISA under the hood. So just kind of to set the stage for what I'm talking about, like typical modern systems on chip, like not necessarily for very, very low power devices, but other IoT-ish devices that you would find on what they call the edge these days, that has some number of CPU cores, potentially GPU, and then perhaps some combination of multimedia encode decode, or a little bit of neural processing unit for inference. And then most of these SoCs will have some kind of subsystem that handles the security, and then the power and the thermal management. And then obviously you have various IO controllers, GPIOs or PCIe, USB, what have you, and then some kind of memory. So, and then all of these kind of get hooked together using either a single network on chip or network of networks. So this is, the typical kind of SoC that you would find, in any Apple, AMD, Intel, chips these days. Same thing with a bunch of the cell phone things, Qualcomm or Samsung, MediaTek. Most of these SoCs that you have will have some architecture that is, that looks like this. If you kind of squint at it, it'll look like this. So what am I saying when each of these SoCs is multi-ISA? So when you think about it, you have one or more CPU cores, and depending on the device, that could be x86 or some flavor of ARM, RISC-V, etc. And then if you have a GPU, GPUs are nothing but like big arrays of SIMD units, which is single instruction, multiple data streams. So these are highly parallel floating point units effectively. And so most of them have vendor specific ISAs. So already if your chip has a CPU and GPU, you have two ISAs right there. And then, so a lot of the other units, like the multimedia engine, for example, could have multiple DSP processors for audio processing, and then for video encode or decode. So they have their own little controller, and that runs its own code. And then the neural engine, depending on whose engine it is, it's a variety of ISAs. Some of them, like for example, some of them use RISC-V. Others have their own proprietary ISAs. Or ISA, by the way, I mean instruction set architecture, for those who are not familiar with that term. I should have set that up in the beginning. And then for the system management, this is what I was talking about for, like thermal management or power management in general. In the past, these used to be done using various hardware state machines, and then they would get inputs from the temperature sensor and things like this. But after a while, they became very limiting, and if you had a bug in somewhere, there's nothing you could do once the chip came out. And then the other problem was that you couldn't really optimize it a whole lot after the chip came back. So a lot of these, there was some limited programmability in terms of registers, but it became very difficult to tune the system for maximum efficiency, as in performance per watt. So most vendors basically switched to using some kind of microcontroller to do this system management. And these could be from ARM, Tensilica, AVR, PIC, any of those that are basically get embedded as IP within the system management subsystem. And so now you've basically taken something that used to be state machine and turned it into code. And so now it's more flexible. You can implement a variety of different algorithms. You could have application specific algorithms, right? If you're playing a game, you choose one profile. If you're running something compute heavy on the CPU, you could choose a different profile. So it becomes a lot more flexible. But that means there's another microcontroller and more code running on that. And then IO controllers have their own microcontroller. So I think if you, just Joe spoke about some of this, like they embed their own microcontrollers in that design, and they run the TCP/IP stack or the whole Bluetooth stack. So they have their own microcontrollers and their own ISAs. So already, if your system has 3 or 4 of these, you're talking of a handful of different ISAs, and so different types of code running within the same system. So where does all this code live? So for CPU, it's kind of obvious. It's in your boot code, and then the OS and all the applications, drivers, everything that you run. For the GPU, the ISA, the code that runs the GPU ISA, that can be included in the driver, or oftentimes it's emitted by some kind of just-in-time compiler. And the JITted code is the one that actually runs on those floating point units in the GPU. For other engines like the multimedia engine or the neural network engine, the code would be loaded by the driver of that engine into the RAM, or sometimes the code can be baked into the ROM within the system. So these snippets or code for these engines would typically, when you install the driver, it gets put on your disk, and then it gets loaded when the engine is initialized. For system management, that code is generally bundled with the system boot code. So like BIOS, for example, or UEFI, or those kinds of platform management code. And this oftentimes will run independently of everything else that the OS is doing. And then there might be other firmware bundled in for other kinds of like the IO controllers and things like that. They may either live in the BIOS or the OS drivers. So it varies. But what all these different ISAs are all running in parallel when you're using your system, basically. And so you might say, like, what is the complication from having these different types of cores, which are different engines running different ISAs? So each of them can have different expectations with respect to memory ordering. Like what happens, if you have a few different memory operations, what should be the relative ordering between them? And each CPU, each microcontroller can have different expectations. And then depending on how the system is designed and how the network on chip operates, some of the cores may have caches, and those will be hardware coherent with the others, and others may not, and may just look like some kind of scratch memory and not be coherent with the rest of the system. So the last level cache and the network on chip and the memory controllers have to understand all these different requirements of each of these sort of subsystems, and make sure that those ordering requirements and those coherency requirements are met. So this is the last slide. Takeaways, heterogeneous ISA chips are in the present and the future. I don't think we're going to go away from that. And you may not realize that any app that you're running on your laptop or phone is inherently multi-ISA under the hood. So that's it. Any questions?
Fascinating. Thank you.
Yeah, thank you, Shankar.
Okay, Kurt, if there's no more questions, you can go next.
Yep. Thank you, Shankar. I know you also have another business meeting
Yeah.
tonight.
I will be around for another half an hour, 20 minutes maybe, and then I have to go.
Okay. Well, we might. I know he only has a couple of minutes worth of material to speak. We might get Brian Smith on here because he, among other things, he is another IoT fester. He was around. I'm thinking IoT Fest 2015, maybe, Brian. And among his other claims to fame is he hosted an Orlando FOSS conference where one of his guests, one of his keynote speakers was BLU's very own Federico Lucifredi. So Brian has a good nose for talent.
Quick note on that. I think I'm in read-only mode today. Rough day at work, so I'm here enjoying the content.
Okay. Well, we'll put on somebody else. Let me see. We actually had way more people say they had they could present than luckily they're all going to be mostly lightning talks. But we're saving them to the end. We're saving Professor Jelinski and his students to the end, and probably DeLacy too. I don't even see him. So I think that either puts Gaurav Mitra or possibly Bob next in line. Bob, do you have a 5 or 10 minutes you can share with us?
Let me turn on. Okay. Well, the talk I have is longer than that, but instead of playing the video, I can do a quick run through and skip over the stuff for this audience. So let me see if I can get PowerPoint to work. And basically, this will be a modified version of my talk, an abbreviated version. So the adventure begins. Share. Let's see. Okay, first. Okay, now, if somebody wants to talk while I'm doing this, I'm still figuring this out, how to do it.
Yeah, go ahead, BD.
Yeah, it looks like Brian.
Oh. It's like, hey, somebody new.
On the side, is there anybody who knows how to share a PowerPoint this way? I can share a video, but the PowerPoint is harder.
At the bottom of the screen, you have a little
Dot.
screen with an arrow.
Arrow? I see dot.
To the left of that, I think just to the right of the camera icon.
Oh, there it is. Okay. Oh, okay, there it is. There's a screen I can share. Share. Is that working?
Yep.
Yeah.
We're working perfectly, Bob.
Okay, I'll give it a try. Okay, as I said, this is a talk I'm trying to prepare, and it's still a draft. So if I can click, no, I got to find the screen. PowerPoint, it works in its own way. Somewhere there's a PowerPoint screen, controller screen. Okay, I'll do it this way. So I won't go. Okay, the main point of this, again, skipping through, is that we encode things with alphabets, that the information is not there, and that the hardware-centric view is about the hardware. And I'm a software guy, so 0 and 1 is just one encoding. But the point is, these are not physical things. So once we get past the limitation of the physical understanding of software, for example, a QR code can connect things just like Wi-Fi. It's the same kind of idea, way we use a medium. So the main potential point here is this agree screen, and most people are not bothered by the agree screen. I'm looking to the side, but that's where it is on my screen. And the difference is those of us who actually build things, our devices can't get past it. So, actually, I should have begun by saying I hate the term IoT. There is connectivity. It's not different from the net or the web. But what is different is that these screens prevent devices from connecting. So this is the key point. This is my home. Actually, it's behind me if you turn the camera on. And it looks messy, but I don't see the mess. I can focus on just two devices and ignore the rest. And that's the key thing about connectivity. I connect things with symbols, and it doesn't matter what all the crap between is. That'll offend the telecom people, but their time is come and gone. And the key thing is that ESP chip, and I hope the TI chip is just as cheap and powerful and more powerful than that, because that's a pretty old chip. So that's what puts intelligence in the devices. And of course, I could take it anywhere in the world and they stay connected. Now, physically, the current internet makes it hard, but I can put shims in to get around that as long as I don't hit those agree screens. And of course, they can be devices. It could be a pill bottle. And the nice thing about that pill bottle as an example is that's a few dollars too. So all the pill bottles you see at CES are very expensive because they have to justify the cost of negotiating. If we take an infrastructure approach, then we remove all the problems of cost of negotiating. And the key thing, getting ahead of myself, is this concept of ambient connectivity, where we can focus on the relation between the devices and not worry about, the technical term is the crap in the middle or the crap between. So this is the old school, where you actually had to send a message between the 2 points and I had to travel the wire. And basically, that's a string between two tin cans, because the phones were no smarter than the tin cans. They were just a microphone and a speaker. And the right model is the post office. You're carrying messages. And telephone calls used to be measured in message units, which are telegrams. So the new model is we have smart sound devices, and we don't need somebody carrying them for us. Instead, we need generic packet infrastructure. And here's the key point. Voice over IP is a fundamental disconnect from what we had in the past. It did not come out of telephony. It does not operate on telecom principles. Instead, we take the word hello, we encode it in packets, throwing away the complete knowledge of the word hello. None of those packets have any meaning. Anybody looking at the packets can't find the meaning there. So you cannot apply a message carrying algorithms or policies. You cannot fix a problem. If you lose a packet, you can't replace it. So none of the very idea, the fundamental concept of telecommunication networks goes away. So if you want to talk about it, use the term IoT. It's about the relationship between the devices without worrying about the crap in the middle or the between. And the phone company could not give us picture phone, even after half a century of trying. Yet the VoIP not only does voice, it does video. So the key thing now, what we need in order to do connected devices, is infrastructure as a resource. That we don't want networking as a service and depending on something in the middle, but instead we want a shared physical infrastructure. But the key idea is that infrastructure is not a network. It is not the network. It's facilities. The networking is what we do with it using software. The internet is one implementation, but anything else can be. So the key thing is that once we have packets, we can do anything. The internet is a good basis because it gives a packet infrastructure, but it doesn't give us stable names. DNS expires, IP address ephemeral. So it's a work in progress. I think it was a transitional form. But the elephant in the room, of course, is that we view it through the legacy of the past. We have these old ideas like stacks. The ISO stack is a terrible design principle. It's what we tell children, but it's not something for real design. And the other thing is 5G that's coming to drag. It's sort of like the hand out of the grave, dragging us back to the past. Because 5G is basically the SS7 model, where the phone companies were charging for network as a service, because the design point of SS7 was to provide a clear path, take the resource away, and what it got in return was circuits busy. So instead of taking a layering model, we take a resource model. And ambient connectivity views all the infrastructure as a resource, and you don't worry about the details. You just design assuming it. Now, so why do we frame today's thinking? Well, if you go back to the 1930 World's Fair, we already had the smart city. It was a central office with index cards. We also had self-driving cars, but the highways were guideways, which is a much better idea than we have now. And then the ultimate design point is the Jetsons, because obviously that's the future. So that's how we got into the term, like maybe LA make load register A and turn to OPCO 75. So it's very close to one-to-one to the machine instructions. And then people started doing fancy macro assemblers. And then they did these programs which could take seeming high-level instructions, but they correspond to machine code. So that's why I call C sugared assembly language. It doesn't get you far enough away from the machine, but it was basically BCPL version 2. Okay, back to the talk. So as I explained, I'll go back one. I don't want to go back more. Telecom was funded by charging for a service of phone calls, and the strain between the two tin cans was a cost center. That model does not work once we have intelligence in our devices. So since the money is not going to pay for the infrastructure, first we tell children stories. You're really paying for a phone call. You're not, but people will believe anything you tell them. But ultimately, we had to drop piles of money on the broadband infrastructure because the old business model didn't work. The answer is not to do that. The answer is to recognize that we have a common infrastructure that we should pay for, just like we pay for sidewalks and roads, the public packet infrastructure. And there's nothing new about a public packet infrastructure because your home network, your campus, your offices are shared packet infrastructures. Now, when you get into this, so this is a slide from My Trilly magazine on all these IoT projects, and this is in India, but it could be anywhere. And it's complicated because you got to worry about which radio, where, and what radio, what characteristics, and everything. No wonder nothing happens. This is far, far too complicated. But we can simplify it if we could just put a Wi-Fi, glue a cell phone to a cow, or maybe you could do a little better than that. Because for lions, they wear collars now with radios, and I think cell phone accounts, because lions deserve a cell phone account. Unfortunately, cows don't, which is a problem with this model. But if we take an infrastructure approach, all that cost disappears. We can put a $2 radio on there, TI or ESP, and we're done. And we can then apply that to many cows. There's no additional cost. We can do tractors. We can drop things on fields. We can do all sorts of things because each of them is a project that an individual or small group can do without having to negotiate, without having somebody second guessing them all along the path. And this is why these small chips, and I look forward to the TI version, are very powerful. And remember, the ESP was a few years old, so we've really advanced a lot since. So the combination means we need a fundamental different approach and infrastructure that enables innovation without having to negotiate everywhere we are for a new account. And remember, it's not just the individual building chips. All those cloud services that complement the local thing, you don't have to. Now, key architects, you don't depend on them, but you can use them. Those are now limited in what they can do because there's a toll booth between the endpoints that's saying, no, you can't do it unless you pay. And 5G is just that toll booth, put back because the internet got rid of it. 5G is trying to put it back. So just say no. So now we can have any number of these devices anywhere and really scale up because we're no longer the traditional limits. And okay, so we can go through the costs. There's basically cost nothing to put this infrastructure in. We're used to giving roads away for free, but when we put broadband, which is cheaper, it's like a payday loan. You can never pay it off. And same for the 5G thing, which is, again, there's a conflict of interest. So the service providers also offering the infrastructure. So a key thing about 5G is they want to put their services, network virtual services and software-defined networks is really a scam to basically have you use their data centers, not other people's. In the meantime, a MIMO radio can cost just, put a Wi-Fi thing up for a few bucks. I put $1,000 to include the people rolling a truck out, putting it up. But basically, you just buy it to put them everywhere, and we get complete coverage. So the trick is to make it happen. And, MIT just have open networking, but people fight. They're scared of it. So the real problem is the POGO thing. We are the enemy because you can implement connectivity locally. You buy a pipe through telecom just as you buy a broadband pipe to connect your house. And then cities can interconnect and they coalesce, and then we achieve flashover, which is an infrastructure. And then all these chips really turn the world into software, and we can just start implementing without having to ask permission. Of course, there's going to be chaos and a mess, but we're getting a handle on how to do it. So some of the legacy ideas like firewalls will keep for a little while to coexist while we create this open infrastructure and then have things connected healthcare and all sorts of innovations. So, okay, so I'm back. And I did that in only 15 minutes.
Yeah, we've got some time. We I told Josh 8:15, so we've still got some time.
Okay, I mean, I raced through. If you want to get a recorded version, which is much longer, because I'm aiming at an audience that does not have as much background, so I go into a lot more detail.
Actually, Bob, do you think you should do another talk on this in April?
What? Do another one?
Yeah, in April we don't have anyone scheduled yet, so
I could. Yeah, and hopefully I might be able to work with the IEEE on a more professional version. But if you want the URL for this version, I really could use feedback. So I put the URL in the chat. But any questions, nostalgia, anything? By the way, you see the table behind me there.
Yeah. No, I did a lot of assembler programming back when.
Yeah, I have to say, I'm scared of assembler now because the chips have really changed their nature with highly parallel and all these things. So, the world of assembler programming has changed. So I think one of the important points about assembler is how simple it was. The 6502 was so simple. I wrote it one night when I was at ECD. The only machine we had working was in New York for a show. So I wrote an emulator that night, debugged my program, which was a fancy basic, shipped it to New York, and it ran.
But didn't those Motorola chips couldn't do division in hardware, right? You had to write something to do division and multiplication.
I don't know. I mean, I was not much of the Motorola chips, but I suspect that there was some hardware assist. The real machine was the IBM 1620 Model 1, which couldn't even do addition. It had to do table lookup to do addition. How many 1620 programs are here? Am I showing my age?
No, my first assembler was PDP-8.
Well, that was a contemporary. That was a little after, but yeah. Actually, I never really did PDP-8 programming. I was familiar with it, but I never really programmed the PDP-8. I don't think I did.
Yeah, I worked at Burger King. We had our point of sale system was PDP-8s. You couldn't see the PDP-8; it was under the table, but
yeah,
PDP-8M.
Yeah, after Dan Bricklin left DEC, he was doing a point of sale system for Carl Jr.'s in the late 70s.
And they are still in business.
Yes. Now, I mean, it's the nice thing, and this is one of the things, is some of us are fortunate to grow up while these machines are very simple. So as these innovations happen, we learned each one. And I don't see how a kid coming up now, when you look at GPT, and you want to say, yes, but if you go down with a soldering iron and work your way up, you can see how all that happened. And you really understand the machine at a deep level. So I've got to say, it's becoming harder and harder to, trace out that path.
I took an assembly class, I think last summer, and the hardest part for me was changing my thinking, and learning how to think how the processor parses instructions. And one thing that occurred to me was that, using today's debuggers, I can't imagine how you would have debugged stuff back in the 80s.
Well, first, one of the programs I wrote was a debugger, which can handle assembly language as well as PL1 and COBOL.
So that would show you where the stack was in the memory, and
well, you can look at it. That was just there. Data. In other words, I mean, if you wanted to see what was on the stack, you just looked at the stack. It was much simpler. Now, I mean, there was some magic. For example, in Visual Studio, the first time I could go back, that was amazing. That you can undo things. But for the most part, I mean, in a sense, right now, if you debug in Node, you can't go back. So you just put breakpoints, you put print statements in. In that sense, it's not that much different. It was just, the main thing is that I'm trying to give the sense of it. A lot of it was your mindset. So you'd think in terms of the operations, and yes, you'd have to put in each of the detailed instructions, but they were idioms. So it wasn't necessarily that much harder. It was just more tedious.
Yeah. Then how many registers did you have to work with?
Well, it's a question. I mean, the number of registers wasn't as much the issue because it was actually 6502, I think, at 2.5. I have to remember, like X, Y, and A indexing, but they're 8-bit. So, you'd also treat other, you use memory more. So, interesting thing on a stack machine, you don't even think in terms of registers. So, it was not a major issue. In fact, on the IBM 360, there was 16 registers, and that was a pain. Because if some fool put something in register 7 and you were looking at a piece of code locally, how are you supposed to know that 10 pages before you, the register 7 was taken? So one of the things about assembly, you rapidly learn to really structure your code. Or at least, I'm sorry, some of us learned. But, other people would say, oh, branch instruction. Who needs to waste a byte storing a flag? I can modify the branch instruction in line. And it took a while to stamp out that way of thinking.
Yeah. Well, I had, when I was at the bank, I inherited a program that was originally written in assembler, an IBM assembler, and converted to Burroughs COBOL. And nobody would touch it. And so they gave it to me. And I looked at it, and I looked at the underlying assembler. It was IBM assembler. I understood what the underlying stuff was. And it was automatic. A lot of the conversion to COBOL was automated. It was not by hand. So it was really, really complicated.
Well, yeah, it sounds like somebody. I mean, if you did a structure assembler, it could be quite messy to translate. But on a Burroughs, was this an Algol machine, or was it an? I'm not familiar with the full. I know Burroughs has some interesting architectures.
No, this Burroughs was an ASCII machine. It was not Algol, and it was designed around COBOL.
Okay. Yeah, I mean, Burroughs did some innovations, and a lot of things in those days. I mean, we look at all the assembler that did, but what was also is that people were experimenting with architectures, like the Burroughs things, and also there's all sorts of. I think with the Precambrian explosion of ideas, because I had a textbook on the history of programming languages. I bought some copies recently. It was about 1 inch thick in 1966. So there are a lot of ideas, and it's interesting to see which ones survived and which ones have come back. Like Lisp has come back. It's called JavaScript.
I didn't know that they were related.
What?
Oh, I didn't know Lisp was like JavaScript.
Well, no, okay. Lisp was followed by Scheme. JavaScript was modeled on Scheme, and then I think was told we can't have all these parens. So then he put a Java-like syntax on top of it to make it friendlier. And one limitation is there isn't a reverse. You can't look at the JavaScript program in a JavaScript program easily to parse it, but that might be coming back. So you will be able to have programs operating on themselves.
One question I have about JavaScript. So, like in the case of like other parsed languages like Python, like you could see memory codes and stuff. Is there some way to see memory allocations in JavaScript, or is that kind of masked?
Now, what do you mean by? I'm curious. What do you mean by seeing the memory allocation in Python?
Like say if I call an object, like if I could see the memory address of an object in Python.
It does give it to you.
Yeah.
Okay. Why? Okay. I know you can't answer that.
I assume that Python is giving you enough control of the system that it will show you the memory addresses of
I think it's more historic artifact.
Oh, okay.
Because if you look at C#, it has both. In other words, you can go to an unsafe mode, pin things to a physical memory address, but that's a transitional form. So the question is, why would you want to look at a memory address in JavaScript?
Yeah, I guess it's more of just if I wanted to play around with optimizations.
That's not the way to optimize.
No.
You optimize by understanding the algorithm. And once you can pin down the memory limit. So there's a whole discussion of the V8 engine. And one of the historic ideas we had in the old days is the machines were very small. So you would pre-compile the programs. You would only load the libraries of things you needed carefully to make sure it all fits in memory. And once you're running, you lost all that. Fortunately, we've grown up. And we compile as just in time, which has a big advantage because you know what's really happening. So the just in time compiler can do better than pre-compiled code. For example, one of the problems with programming, you have all these edge cases. Well, if you're doing dynamic compilation, you can see the edge cases aren't there. If the edge case comes up, then the compiler will handle it. Otherwise, you can optimize past it. So a lot of advantages to just in time. And because we have the full facilities available, we can have a lot more flexibility in programming, but it's very hard to wrap one mind around it because we're still suffering the trauma of the old days. Just like people are pathologically afraid of null because in C null was so dangerous, but today it's a very useful value to use. Unfortunately, people have not gotten over the fear of null.
Yeah, why is null an object and not a primitive?
Why is null an object and not a primitive? Well, it depends on the language, but basically it's the null object. It's like, why is 0 not a number? It is a number. And if anything, fear of null and fear of 0 are the same. So the people who want to get rid of null should also get rid of 0 for math because 0 is a really.
I think that null is best replaced by something like an optional type, which can be either something or nothing.
Yeah, so why not just call it null? Like it's just changing the name doesn't.
Well, no, but an optional type actually contains the type of what it contains, and it's the problem with null is when you don't expect it to happen. It's not in the type.
But why is the type intrinsic? Type is not intrinsic. I mean, that's another thing. The whole static type languages was a traumatic phase we went through.
Well, I don't know. I'm very into Rust, and Rust is statically typed, and it lets it do some interesting things with the compiler and optimization and stuff.
Yeah, and Rust is a throwback. I can understand some of the use for Rust, and one day I'll learn it. But right now, work fine without it. Just so you're right in the sense null doesn't know its type, but any type in JavaScript doesn't really know its type. You look at on the ground what it is. So to have nothing, how many? I have nothing of what is an interesting philosophical question.
Well, yeah, and it ends up meaning that like if you replace null with optional types, then it's just it prevents. There's some really poor design choices that can come from null, and then if you're using someone's library and it uses null in an unexpected place, and it's like then you know, and you don't expect that an empty text field causes this library to emit a null somewhere.
Well,
And you don't test for that, and then now you have a null somewhere in your application, and it just says, and there's just an error referring a null, and it doesn't say, you know.
But that's a general problem of, you know, traceability. But the flip side is use TypeScript and things like that, which will sort of keep sort of the meta knowledge around at a meta level without having the runtime worry about it. But you know, but if libraries fail, I mean, there are all sorts of things. Like you pass a -1 to square root, you know, what's going to happen?
Okay. Enough learning for one night. We're going to have to.
Okay, back when I was a kid. Okay,
we're going to have to pass the stick to DeLacy, I think, because
I was never a kid. But
he has a couple. I think a lightning talk, but maybe a little bit longer. Either way, we'll do him, possibly Sean Nishi, and then to Professor Jelinski.
Brian connected? I don't see him in the list here. Oh, BD is Brian?
Yeah, but can you hear me there?
Oh, yeah.
Hey, Bob, thank you very much. As always, it's you're an impossible act to follow, and it's wonderful just to hear you talk anytime you get the opportunity. So thanks for doing that. I'll just kind of breeze through some slides here if I can toggle them up onto the screen. Let's see if I start sharing a tab. Maybe it's
Bob, can you unshare, please?
Is he good there?
Yeah, we're good. You should be able to share.
Yeah, that's interesting. You can't. Let's see if I can do this. Can you share across browser, or do the tabs have to be in the same browser?
no, I was sharing different windows totally outside the browser.
Gotcha.
And there's also, I discovered you can share the YouTube, also has a direct YouTube share.
Let's see if I can do that way.
Where things are in the user interface is another question, but you can do the stuff. So it's actually nice. This is working much better than it has in the past as I learn more about it.
I'm not sure those are my dogs, but that's God knows what we're going to see here. That's. I wonder if I can jump over there. That's interesting. Oh, that might be. All right, give me a minute here. I got to switch user IDs to make this magic work, I think. See if that works for. Okay, let's see. View slideshow. Okay, do you see a slide there now? 15 minutes of fear.
Yep, that's it.
Great, thanks. Sorry about that. So basically, it didn't, for me at least, let me share between two different browser incarnations and stuff. So anyways, the slide is 15 minutes of fear, the hunt for virtual gold, which I borrowed from Bob's quote there about crypto. And so what inspired this kind of brief, lightning talk were these two stories, articles, one by Ken Thompson, whom I know everybody is, I presume everybody's aware of, and my guess is Bob probably personally knows, and Russ Cox. Russ Cox, who I think may be somewhat less well known, he may even be local. He works at Google currently and has been a cornerstone of their Golang effort. But has anybody read the Reflections on Trusting Trust article by Thompson?
A long time ago.
Yeah, I figured Bill would have. And it was written a long time ago, August 1984. Bill, this is a challenge, but
I believe I was in the audience when he won an award for it.
He did. And so the gist of it basically is that he talked about the challenges of trusting code, what the code does, and of course, some people are better at doing wild things with code. But effectively, what this paper is about is going in and not only changing the code to put backdoors into it, but changing the compiler. People were talking about assemblers and binary code. I mean, Bob probably more than anybody remembers the peek and the poke of the early days of the apples. But so Thompson talked about the risks associated with, and it's kind of coder beware. So this is a graphic for anybody. I won't pry to find out if people actually own crypto, but I presume most people know what crypto currency is. Crypto is a lot of different things, and one of which in its applied form is currency. So, or pretend currency or digital gold or anyways, a lot of it has been stolen. A lot of it has disappeared. The fabulous story about the guy who, what did he put up millions of dollars for people to help him find his hard drive because he dumped his hard drive into a kind of a landfill, and it had all his magic keys on it too. So this is a bit of a lead-in prelude to a talk in March about cryptography, tinkering with crypto, and in fact, Google's libraries, which are named Tinker. So anyways, over this period of time on the slide, a lot of money has disappeared. And the thing that ought to be visible from these slides is that the frequency, and which keep disappearing for me, I don't know if they do for you, but the numbers have just grown enormously. So to some extent, in the context of Thompson and Cox, how do you manage this? So I put this out there. This is just literally the slide on the left is from today. Fidelity, which is one of the mainstream companies that has actually invested in technology in and around crypto, one of the credible big name firms, is just scaling back its investment pretty precipitously. And if you've been following any of that end of the digital currency news, they are not alone. Does anybody know what this the event stream hack was? And Bob had mentioned Node, and anyways, the brief story of it is that a whole bunch of crypto was taken from people who had relied on some Node JavaScript-y stuff. And what happened is, a bad hacker worked their way into actually becoming a maintainer on the Node, one of the Node libraries that turned out to be critical to this one particular cryptocurrency. And so they went to, this is obviously well planned. There was a whole buildup. They became the maintainer, and then they put surreptitiously code in, which only attacked actually the cryptocurrency that this one particular area, even though this library was used widely, they limited the hack to just this one code currency application and also the big accounts. So anyways, does anybody know what FTX is all about? Actually, does anybody know the principles in FTX? At least
Well,
one
it's
of
just
them.
that they took customers' money and then gambled with it through speculation.
For FTX?
Yeah.
Well, so FTX is going through a bankruptcy proceeding right now. Somewhere depending upon the
As
number.
Ponzi schemes do.
As Ponzi schemes do, right? Bill is, by the way, I haven't put it in the slides because I haven't got Bill's permission, but there's going to be in March some kind of a Ricker test, which is sensibility as to the security. And the way this ties into when Kurt and I and Bill and a few other people with the support of TI, did the first IoT Fest. A lot of it was about making things small and doing things economically at kind of at the edge and Bob gave a presentation, as did others. What this tie-in is about, and Bob kind of referred to it, I think, earlier, was what happens to the data, the local IoT data when you push it out to the cloud. And anyways, this FTX, which was a cryptocurrency firm with, a number of principals with some form of affiliation to MIT and some local and some West Coast. Anyways, it's going through bankruptcy right now. A number of the people have already pled guilty, and a few other high-profile people are holding out. But if you see in the upper right-hand corner, it talks about this in the white block of outside of AWS. Anyways, there were some back doors. And so there were private keys and there were kind of off ledger transactions reported, which could be of, sort of certainly six figures and probably closer to, to $1 billion. Okay. So now here's the transition to the IoT angle on this. Let's move to Iowa. So I don't know if people know about Google Cloud, but again, the question is, well, you've got all this IoT stuff. Where do you push the data and where do you store the data? And back when we did the IoT Fest, there was really I don't know how big AWS was at the time, but the whole cloud phenomenon has come along since then. Anyways, the Tau offering from Google Cloud is on ARM servers. And Shankar probably has ducked off at this point, but the first Tau servers that Google did were actually with AMD. And the idea was to come up with higher price performance and energy efficient server offerings in the cloud. And so for everybody to take notice, there's a terrific free trial available from Google right now. Ampere is the people who make these ARM chips that Google has partnered with. I don't know what the overlap is. I'm presuming there is some close confabulation of the leadership of these firms. But anyways, and it's a generous credit in terms of dollars and duration, like 90 days. So I just signed up for this thing today, basically got the basics up and running, and we'll talk more about this in March. This goes through at a high level. It does give you a programming software shell coding environment that has kind of reverberations of Microsoft Studio Code stuff. The whole G Cloud thing is a little bit, for me, there's a lot of overhead, frankly. If you've used DigitalOcean or some of the other, Vulture, I think is more akin to this. You're more in the realm of SSH and other traditional Linuxy standard tools to manage these cloud services. On the other hand, obviously, what Google Cloud and AWS offer is lots of tooling. And I won't get into AWS, though I've used it. And so far, the Google Cloud thing is pretty good. A lot of keys floating around. How do you manage them? When do connections work? Okay, so the other thing, Shankar did sort of the hardware version of the different architectural models, and this is how it shows up in software. This is the Golang compiler, and as you can see, lots of different hardware architectures, lots of different OS combinations, and pretty remarkable that the stuff all runs. Again, we've got this challenge, I think, of how do you do stuff cross-platform. This talks about, I made some goofs today where I just visually skimmed, and if you see the block that's circled in red, that's framed in red, you see AMD, and of course, coincidentally, it's AMD is the same 3-letter spacing as ARM, and so you got to make sure you get the right ones. This one thing that's really good about Google Cloud, and there's no reason why people shouldn't try this. First of all, it's free. Second of all, they promise that they're not going to charge you in the event that you run over their generous allocation of funds, which is good news. But additionally, very good online documentation, easily searchable. And okay, here's the free trial. I'll be honest with you, I still haven't completely figured out if they've got a separate Tau free trial, which is for the ARM-based server nodes. They have, you'll come to find out if you've done stuff with the cloud, there's this whole range of hardware you can choose from. But the Tau ARM offering is basically only available, it seems, generally from the Iowa cloud farm that Google has. Jump ahead. This is the Ubuntu, which again, not only do you have different flavors of chips, but you've got different flavors of operating system. I went with both Debian and Ubuntu, but I know people in the group use Red Hat and other things. So they've got a bunch of images, but not every image is available for every hardware. This gives you some pricing information. I haven't done but I hope by March to have. We need a configurator that helps you project what the cost of your cloud usage is going to be. And I'm hopeful I can do this on the Google Cloud stuff. I was less successful on other platforms. The future really is, the present is living in the cloud. This is just, let's jump ahead. Am I going backwards? I'll get to, okay. So I guess just to kind of call it a wrap, if there are any questions, I would be curious if people have tried Google Cloud, if people are using it currently. And the crypto stuff is in some sense a whole nother thing. But the beauty of the software that's available today, crypto for one is one example, is that people are rolling these things out with JavaScript, with Go, with Rust, there's just really a lot of choices. So a question out to the group: have people used the Google Cloud for experimentation or actual production?
I've been using DigitalOcean, and you inspired me to see if I could spin up something Google Cloud, but I'm trying to figure out how to create an Ubuntu machine.
Yeah, to me, I kind of did. It took me a half a day to get my way around. And DigitalOcean, frankly, I probably spun that up more quickly. Some of the differences are Google and AWS, they enforce the firewalling stuff and these other things, whereas DigitalOcean, you're much closer to metal, as people talked about. You're installing there are kind of pros and cons.
That's a major feature for me, because I'm running just want simple machines for simple purposes. One of the things, by the way, DigitalOcean offers you is a Mastodon install.
I had not seen that. They have
a lot of canned applications that you can just plug in.
So yeah, I think I looked at, like, I was originally Microsoft and Amazon, and they're far more complicated. Now I don't know where Google is. What I liked about DigitalOcean is you can do simple things simply.
Yeah, and the other thing is you can get in pretty cheap on the DigitalOcean front, and they do have good support for out of the box kind of applications as well. the once you start dropping on databases and other things, all of these services really start hitting you. The beauty of and kind of the bottom line message from the opening slide in all of this is that as we all have kind of benefited from the open source world, and there's a lot more plug and play, whether it's with Node or whether it's with libraries. Russ Cox, a lot of the stuff he was talking about was essentially better control of your source code. But the problem is every one of those open source libraries that you roll in to your most cherished app really become, vectors of exposure to downstream or upstream hacks, right? So you may not have to worry about that or deal with that if you're just looking to offload IoT data, but that's kind of the big message, which is how do you protect yourself from, essentially people who are hacking for a living? And if you're not transacting money or virtual gold, maybe it's not a big deal. If all you're tracking are, where the cows are going and when, maybe you're not going to be as exposed.
That's a deeper discussion of what kind of attacks you're protected against, because and this is a longer discussion, that the problem with the firewalls is once you breach it, you're wide open. Now, by the way, one problem I had was a conference where I was speaking to people about the security issue, and I mentioned I joked about how well the Maginot Line worked, and then I realized nobody in the room knew what a Maginot Line is. How many people on this talk know what the Maginot Line is?
Absolutely.
Absolutely, I know it too.
I know, but the kids don't. You can't use the reference. So that
and unfortunately, it's a dangerous reference because a lot of people think it didn't work and it worked.
No, it didn't work. No, it was what made France so vulnerable. Andre Maginot made one strategic error.
No, the problem with it was Belgium didn't build and defend their portion of it and would have gotten offended if France had extended the line behind Belgium. Well, the Maginot Line worked where it was built.
Yeah.
Well,
the tanks diverted around it instead of going through it. It worked.
Okay.
So my point is that everybody, including you, gets it wrong.
No. Well, okay. Let me just
again.
No, whether they of course they went to the weak points. They didn't go directly to the Maginot Line. Whether it could have worked on their terms then is an open question. But the real failure was depending on it, and the mistake
the failure was depending on Belgium.
No, no. The real mistake Andre Maginot made was dying. But she said, by the way, you also need an army. This is not a replacement for an army. So the Maginot Line created complacency. So whether as a wall it would have worked, we can argue about.
You won't have an argument with me because I won't argue it with somebody who isn't a military historian. But you are correct that the politicians were the failure. You are correct there.
So so I'm not going to argue whether the line could have worked, but you're right that the complacency was the real problem.
So as far as the this question about open source and how it's used, the Golang language and the development environment, and I mean you see it now in Git, and everything has their hashes and they're checking all the SHAs, and there's a lot more focus and energy behind making sure that the stuff that you're editing and changing and rebuilding, recompiling is predictable and reliable and well known. But it does come at a cost, and so it's probably a cost that people are realizing more presently because of the essentially the incursion rate into your peace of mind through these various hacks that actually have occurred and are occurring with increasing frequency.
Okay.
But thank you for the time to chat. I appreciate that.
So that's all of our scheduled speakers, unless Sean has an update for us, and then we'll pivot to Professor Jelinski and his students. Do you have anything, Sean? No, he's probably still driving.
We'll have to schedule him in for next time.
All right. Thank you, Brian. Yeah, you're up. So, Jerry, is it okay if we turn off recording for the students because they might be using this material in their classes?
Yeah, I'm wondering if Jerry fell asleep. He doesn't seem responsive right now.
No, I didn't. Somehow I couldn't get my system back online here.